Hi everybody, welcome to the start of our next unit in regular non-AP physics about momentum and impulse and conservation of momentum. Momentum is a term that you have undoubtedly heard many times before in your life. A lot of times they will talk about it in terms of sports. For example, a certain team has a lot of momentum, or a car has a lot of momentum. Long story short, momentum tells you how difficult it is to stop an object. Now, notice that this is reference frame dependent. I mean, if I'm running with a car that is going at the same speed as I am, then according to me, that car is already stopped, so there's no need to stop it. But according to somebody on the ground, that car has momentum. In other words, it is something that could potentially be stopped, and you would need to apply a force against it in order to stop it. So the larger an object's momentum, the more difficult it is to stop it in that particular reference frame. The formula for momentum is P equals mv. So we don't want to use the symbol m for momentum because that's already taken by mass, and silly people might be tempted to cancel mass in the equation and you'd get v equals 1. Yay, we're done with all physics problems forever. No. So we use a different symbol, so we use the symbol lowercase p for momentum. And notice this is a vector. It is dependent upon direction, and it actually is not just dependent on direction, but a vector in the true sense of which vectors behave like vectors. So not only does it have a magnitude and direction, but it also transforms according to rotations of coordinate systems correctly and stuff like that. So that need not concern us. What matters for us is that the direction matters. The units for momentum are kilogram meters per second. So that's just, there aren't any cute little names for these units, but they are easy to remember. You just have to remember the formula P equals mv. And if you're working in multi-dimensional problems, then you can resolve momentum vector components into x, y, and z components, etc. But for the purposes of this video, we're just going to be working in one dimension. And as I mentioned, there's no special name yet for momentum units. There's no need, really. It's just kilograms times meters per second. Makes it really easy to remember. However, something that we'll discuss later, not in this video, but in the next one, is that kilograms times meters per second are almost force units. They are almost force units, because after all, a Newton, F equals ma, so the units of Newtons would be Newtons equals kilograms times meters per square second. So if there was a squared on that seconds, these would be newtons. So apparently somebody took a newton and multiplied by a second. And indeed, a lot of times when we express momentum units, we will actually write them as newtons times seconds instead of kilograms times meters per second. The most basic way is kilograms times meters per second, but newtons times seconds is often more useful, especially when we're talking about changes in momentum, that is, impulses. So let's take a look at a quick example. Calculate the momentum of a 173 kilogram troll running toward the right at 4 meters per second. Well, we write our givens like good physics students because we want to earn all of our points. So we have our mass. Notice the plus sign in front of that velocity indicating that it's going toward the right. Unless otherwise noted, the right direction is going to be positive, up is going to be positive as well. And if we had to work in 3 dimensions, we would also say coming toward us is positive. But anyway, up and to the right are positive directions. So if it's going to the right, that's in the positive x direction, and this is just an x direction problem, so we'll just call it plus 4 meters per second. P equals mv. Notice this time we got rid of our vector symbols, that bold that we often use to denote vectors, because since this is just a one-dimensional problem, it's only going to be the horizontal direction that's going to concern us. That is what we usually call the x direction. So we have P equals mv, plug in the mass, plug in the v, notice the plus sign is there in the given, and the plus sign is there in the answer. P equals plus 692 kilogram meters per second. In other words, we would say that this troll's momentum is 692 kilogram meters per second toward the right. So yes, again, the direction matters. How about another quick example? A weasel is chasing a chicken. Sneaky, sneaky, sneaky. So you have a 0.35 kilogram weasel running toward the left at 5.8 meters per second. Calculate the weasel's momentum. Well, we write our givens. Notice the minus sign in front of our velocity. Now, you might think like, oh, just one object, who cares? Well, In the next video, we're going to be looking at collisions between two or more objects, in which the direction will obviously matter. It's going to be a very different collision if there are two objects going toward the right, where one is going at 11 meters per second and the other is going at 12 meters per second, and there's just this kind of relatively slow collision from their point of view, compared with one going to the left at 11 meters per second and the other going to the right at 12 meters per second. That's going to be a much more explosive collision. So yes, the direction definitely matters. We have a minus sign here. Plug in our formula, P equals mv, plug in our givens with units, and then we get our answer with units of negative 2.03 kilogram meters per second. So we would say the weasel's momentum is 2.03 kilogram meters per second toward the left. So again, that direction being very important again. What about a change in momentum? The change in momentum is where we're starting to realize, okay, there must be something else going on. So let's say I shoot a 0.003 kilogram rubber band, that is a 3 gram rubber band, toward the right at 35 meters per second. It bounces off a wall at 3 meters per second. Calculate the rubber band's change in momentum. Well, here we have our givens. There's our mass. We have our initial velocity. We have our final velocity. Notice that since it was initially going toward the right, we have a plus sign there. It ended going to the left with a minus sign, because left is negative, right is positive. Delta P is what we're trying to find, the change in momentum. Well, what does change in mean? It always means final minus initial. So whatever comes after the delta sign, the capital Greek letter delta, we want to do final thing minus initial thing. So delta P is final momentum minus initial momentum. Well, what's that? Well, everywhere I see a momentum, I know that P equals mv, so I'm going to plug in mv with appropriate subscripts on my v. The mass doesn't change for the rubber band, hopefully. At least, obviously, not appreciably. So there we have it in terms of m and v's. Now, we can make things a little bit easier and factor out a mass. That'll make our math a little bit simpler, fewer things being plugged in. Just make sure to use your parentheses in the calculator. So we plug in our mass, we plug in the final velocity, we plug in the initial velocity. And notice we get a change in momentum of negative 0.114 kilogram meters per second. Notice the magnitude of this is a lot smaller than it was for the weasel or for the troll. A lot of that has to do with the fact that weasels and trolls have much more mass than rubber bands. It's harder to stop something that has more mass, even if it's going slower. But if something is going fast enough, even with small mass, it can still be pretty hard to stop. So there we go. We have a change in momentum of negative 0.114 kilogram meters per second. The negative denotes that this change happened toward the left. As we will soon discover, what is required to change an object's momentum? Well, what's required to change an object's velocity? An acceleration indicates a change in velocity. What's required to cause an acceleration? Well, we know if F equals ma, Newton's second law. So a force is required to cause an object's velocity to change, which means a force is required to cause an object's momentum to change. And since the change in momentum is negative, that means the force was negative, i.e. the force must have been toward the left. We're going to explore that in a lot more detail in future videos. So long story short, rubber band's change in momentum, which we'll later call the impulse, is 0.114 kilogram meters per second toward the left. Now, realizing that forces result in changes in momentum, Newton also realized that there's this third law: every force results in an equal and opposite force. Well, he got that from understanding that in any collision, total momentum must be conserved. This was known as a law of nature even before the works of Isaac Newton. And this conservation of momentum is something we will discuss in more detail in the next video. So, hope to see you then, and thank you for watching.